Not long ago, astronomers noticed something that did not immediately look dramatic, yet quietly challenged one of the most stable assumptions in modern cosmology. A galaxy so massive, so orderly, and so old that it appears to have formed at a time when the universe should not have been capable of building it. According to our best models, the early universe was sparse, chaotic, and still assembling the invisible scaffolding known as dark matter, the very structure required for large galaxies to emerge. And yet, this object already shows signs of maturity, containing stars that had formed, aged, and settled into a system larger than our own Milky Way, all within a cosmic window that should have been far too short. At first, the observation was treated with caution, then with skepticism, and finally with increasing discomfort, because the more carefully it was measured, the more stubbornly it refused to fit. This is not a story about a single strange galaxy, but about what happens when an observation quietly exposes the limits of the framework we use to understand how the universe builds anything at all, raising a question that is simple to state, but difficult to escape. What if the universe learned how to form structure before we think it was ready? For decades, this framework seemed almost unshakable, because it rested on a sequence that felt both logical and unavoidable. First, dark matter slowly clumped under gravity, forming invisible halos. Then gas fell into those halos, cooled, ignited stars, and only much later assembled into large, structured galaxies. In this picture, time was the critical constraint. The universe expanded, matter diluted, and structure emerged gradually, step by step, never skipping ahead. Early galaxies, according to simulations, were expected to be small, irregular, and short-lived, more like cosmic sketches than finished systems. Massive galaxies required patience, billions of years of mergers, accretion, and feedback balancing star formation against gravity. This hierarchy became a cornerstone of modern cosmology, not because it was elegant, but because it worked remarkably well across many scales, from galaxy clusters down to individual stellar populations. It explained why the night sky looks the way it does, why galaxies have characteristic sizes, and why dark matter appears to dominate the cosmic architecture without ever revealing itself directly. Observations from earlier telescopes consistently reinforce this narrative, showing fewer large galaxies the deeper we looked into cosmic time, as if the universe itself were rewinding its construction process. In that sense, the model did not just describe galaxy formation, it quietly defined what was allowed to exist at different moments in cosmic history, setting boundaries that few astronomers seriously expected to be crossed so early. That expectation held until observation itself quietly changed character, not through a dramatic discovery, but through a shift in how deeply the universe could be examined. When new instruments began observing the early cosmos at wavelengths unreachable before, astronomers were no longer limited to seeing only the brightest, most chaotic fragments of young galaxies. Instead, they could detect faint, red-shifted light that carried detailed information about stellar ages, chemical composition, and mass. What emerged from these measurements was not a blurry hint, but a consistent signal pointing towards something unexpectedly complete. The galaxy in question was not merely large, it exhibited a stellar population that implied rapid, efficient star formation, followed by an abrupt slowdown, all occurring within a time frame previously considered insufficient. Spectral signatures suggested stars that had already evolved past their most active phases, meaning they must have formed even earlier than the observation itself implied. This was not a single data point flirting with statistical error, but a convergence of independent measurements that agreed too well to dismiss. The deeper researchers looked, the more uncomfortable the implication became. The early universe was not only forming stars quickly, it was assembling massive, stable systems, while the underlying dark matter framework was supposedly still under construction. Each refinement of the data reduced uncertainty, yet amplified the contradiction, because the galaxy's mass, age, and apparent calmness all pointed toward a level of organization that simulations said should not yet be possible. At that point, the problem stopped being about a rare anomaly and began to resemble something more unsettling, a signal that the sequence we rely on to explain how cosmic structure unfolds might not be as rigid or as slow as we once believed. At this stage, the tension becomes impossible to smooth over, because the contradiction does not live in the details, but in the foundation itself. If such a galaxy truly existed so early, then either the dark matter halos formed far more quickly than current models allow, or galaxies learn to assemble mass without waiting for those halos to mature, both options carrying consequences that ripple outward. Dark matter is not just an accessory in cosmology, it is the load-bearing structure. Remove its slow, hierarchical growth, and the entire timeline of galaxy formation begins to slide. Simulations tuned to match the large-scale structure of the universe rely on this gradual buildup to explain why matter arranges itself the way it does, why voids exist, why filaments stretch across hundreds of millions of light-years. Yet this object appears to have bypassed that order, reaching a state of maturity while the cosmic scaffolding was supposedly incomplete. Attempts to explain it as an extreme outlier run into a different problem: the statistics. If even one such system can form, then the conditions that allow it must exist. And once conditions exist, rarity becomes a fragile argument. The more carefully researchers tested alternative explanations, dust obscuring younger stars, unusual stellar populations, measurement biases, the less room there was to maneuver. Each fix required assumptions that strained other observations, trading one inconsistency for another. The paradox sharpens because the galaxy does not look violent or transitional. It looks settled, as though it has already passed through its chaotic youth and arrived at a stable phase while the universe around it was still turbulent. This flips a quiet expectation that has guided cosmology for decades, that time itself enforces order, that complexity must wait its turn. Instead, the data suggests a universe capable of organizing itself locally, rapidly, and perhaps unevenly, raising the possibility that the early cosmos was not simply younger, but fundamentally different in how it converted matter into structure. If that is true, then the problem is no longer how this galaxy formed, but whether our notion of cosmic evolution has been constrained by assumptions that felt reasonable, worked well enough, and yet may have been incomplete from the very beginning. Once this possibility is taken seriously, its consequences spread far beyond a single object, because galaxy formation is not an isolated process, but a chain of interdependent assumptions linking dark matter, star formation, feedback, and cosmic time. If massive galaxies can appear earlier than expected, then either dark matter behaves differently under early universe conditions, or the relationship between dark matter and ordinary matter is less deterministic than we assume. One implication is that dark matter halos may collapse faster or more efficiently when the universe was denser, altering the pace of structure formation without rewriting gravity itself. Another, more unsettling option is that baryonic matter, the atoms that make stars and gas, may have been capable of organizing and cooling with far greater speed, temporarily decoupling from the slow rhythm imposed by dark matter. In that case, feedback processes thought to regulate star formation, such as radiation pressure, supernova explosions, or black hole activity, would have operated in a regime we have barely explored, allowing galaxies to burn bright and then shut down before models predict. This would help explain why some of these early systems appear dormant, having already stopped forming stars while the universe around them was still highly active. But this solution carries a cost, because it forces revisions to how we interpret the mass, brightness, and evolution of countless other galaxies observed at similar distances. The ripple extends further still, into measurements of cosmic expansion and the distribution of matter on the largest scales. Many cosmological parameters are inferred by matching simulations to the observed population of galaxies across time, assuming a predictable growth pattern. If that pattern is more flexible, then some of our precision may rest on coincidence rather than certainty. Even the nature of dark matter itself re-enters the discussion, not as a passive background ingredient, but as a substance whose properties might vary subtly with environment or epoch. None of these ideas overthrow the existing model outright, but each one loosens a constraint that once felt firm, suggesting that the early universe may have explored pathways to complexity that later became inaccessible, leaving behind a small number of objects that now appear anomalous, only because we are trying to explain them using rules that emerged after their moment had already passed. Faced with this growing tension, researchers have not settled on a single explanation, but instead explored a landscape of competing hypotheses, each attempting to preserve as much of the existing framework as possible, while accounting for what should not exist. One line of thought suggests that the galaxy is not unusually old, but unusually deceptive, its light shaped by extreme dust or exotic stellar populations that mimic age and mass. Yet this requires finely tuned conditions that would need to repeat across multiple systems now being reported, turning coincidence into an unlikely pattern. Another proposal shifts the focus to star formation efficiency, arguing that early galaxies may have converted gas into stars at rates far beyond anything observed today, briefly overpowering the regulatory processes that normally slow growth. But this creates a different difficulty, because such intense activity should leave behind signatures of violence, outflows, turbulence, chemical fingerprints that are not clearly present. A more radical idea revisits dark matter itself, not discarding it, but modifying its behavior, suggesting particles that interact weakly with themselves or cool differently in the dense early universe, allowing halos to assemble more rapidly than simulations predict. This approach can ease the timing problem, but it risks disrupting the delicate agreement between theory and observation on larger cosmic scales. There are also hybrid scenarios, where early supermassive black holes accelerate galaxy growth before quenching it, compressing billions of years of evolution into a remarkably short span, only to shut everything down abruptly. Yet even this requires black holes to grow implausibly fast, raising questions that mirror the original problem rather than resolving it. What unites all these explanations is not confidence, but compromise. Each one solves part of the puzzle while introducing new uncertainties elsewhere, suggesting that the issue may not lie in a single missing ingredient, but in how the ingredients are assumed to cooperate. Instead of a neat hierarchy governed by time alone, the early universe may have been a landscape of competing processes, where local conditions briefly overpowered global rules, producing structures that look premature only in hindsight. If so, these ancient galaxies are not anomalies to be explained away, but reminders that the models we trust are optimized for what survived, not necessarily for everything that once briefly emerged. What becomes increasingly clear at this point is that the boundary of the problem is no longer theoretical elegance, but observational reach, because much of what would decide between these ideas lies just beyond what we can currently measure. Astronomers infer ages, masses, and histories indirectly, translating faint light into physical narratives through models that are themselves built on assumptions tested mostly in the later universe. In the earliest epochs, those assumptions may bend. Stellar populations could evolve differently under denser conditions. Chemical enrichment may proceed along unfamiliar paths, and feedback processes might not scale smoothly backward in time. Even dark matter, though invisible, is constrained through its gravitational imprint, not through direct detection, leaving room for subtle behaviors that escape present instruments. The challenge deepens because the most decisive evidence would come from resolving individual stars, internal motions, and precise chemical abundances within these ancient systems, tasks that strain even the most advanced telescopes. What we see now is an integrated glow, averaged over immense distances and cosmic time, a signal rich in implication but poor in specificity. This creates a peculiar asymmetry. The more profound the question, the more it depends on measurements we cannot yet perform. Future observatories promise sharper vision, but even they will confront fundamental limits imposed by distance, redshift, and cosmic opacity. In that sense, the early universe resists interrogation not out of mystery, but out of geometry and physics. We are trying to reconstruct a fast-moving process from a single frozen frame, long after the moment has passed. That limitation forces cosmology into an uncomfortable position, where models must extrapolate beyond the regime where they are well tested, and where absence of evidence can masquerade as confirmation. The existence of these massive early galaxies exposes that vulnerability, reminding us that what we cannot measure often shapes our confidence more than what we can. Until observations catch up, the question remains suspended between data and interpretation, not because answers are unreachable in principle, but because the universe has placed its most revealing clues at the edge of our ability to see, leaving us to wonder whether the gaps in our measurements are merely temporary blind spots, or signs that our conceptual map of cosmic history still has entire regions left uncharted. As the discussion moves beyond instruments and models, it inevitably begins to touch a deeper layer of uncertainty, one that is less about missing data and more about how scientific understanding itself is structured. Cosmology is built on the idea that the universe can be described by a small set of principles applied uniformly across space and time. Yet these early galaxies hint that uniformity may be an approximation rather than a rule. If the universe can briefly operate under conditions where familiar hierarchies collapse, then the question shifts from what happened to why our frameworks struggle to accommodate it. Models are not neutral mirrors of reality. They are compressed representations, designed to capture dominant patterns while discarding complexity deemed secondary. That strategy works remarkably well once systems settle into long-term behavior, but it becomes fragile near origins, where small differences can cascade into entirely different outcomes. The early universe may have been such a regime, not governed by steady averages, but by transient episodes where local physics briefly outweighed global order. In that light, these galaxies may not be violating the rules so much as revealing that the rules we emphasize were never the only ones in play. This raises an uncomfortable possibility, that much of cosmic history is filtered through a survivorship bias, where the structures that endure define the laws we infer, while those that formed too early, too fast, or too differently are treated as exceptions rather than clues. It also reframes the role of dark matter, not as a single explanatory anchor, but as one element in a network of processes whose relative influence may shift with context. The same substance that dominates structure today may have been only one voice among many in the universe's formative moments. If so, then understanding cosmic evolution is not just a matter of pushing observations further back in time, but of questioning whether time itself plays the same organizing role we assign to it now. The deeper issue is whether our picture of the universe is shaped more by what is fundamentally true or by what is easiest to model, measure, and generalize, leaving open the unsettling thought that the earliest chapters of cosmic history may not fit comfortably into the narrative we have been telling, not because they are wrong, but because they ask us to rethink what it even means for a model to explain a universe that may have learned how to organize itself in more ways than one. Seen from this angle, the puzzle does not resolve into a single missing parameter or an overlooked mechanism, but instead opens into a space where certainty thins out rather than sharpens. The existence of these early massive galaxies does not force an immediate rejection of modern cosmology. Yet it quietly undermines the confidence with which timelines, sequences, and causal priorities have been assigned. They suggest a universe that may not have progressed in a smooth ascent from simplicity to complexity, but one that experimented early, producing structures that condensed, stabilized, and even shut down before the larger cosmic environment settled into the patterns we now observe. In such a universe, some outcomes would appear premature, only because they did not persist long enough to shape the averages we later encoded into theory. This reframing carries an unsettling implication, that our understanding of cosmic history may be biased toward what lasted, rather than what was possible. The earliest universe might have hosted modes of organization that were efficient, brief, and locally dominant, leaving behind only rare survivors that now appear as anomalies. If that is the case, then the question of how these galaxies formed becomes inseparable from a broader uncertainty about how much of cosmic behavior has been filtered out by time itself. We are attempting to reconstruct a story written in layers, where entire chapters may have been erased, not by violence, but by irrelevance to the long-term structure that followed. What remains observable is not necessarily what was most natural, but what was most stable. And if stability, rather than inevitability, determined what endured, then our models may describe not the full range of cosmic behavior, but a narrow corridor through it. The ancient galaxies illuminated by new observations do not close this corridor, but they hint at parallel paths that briefly existed alongside it, paths we are only beginning to glimpse. Whether those paths demand new physics, revised assumptions, or simply a deeper tolerance for complexity remains unresolved, suspended between what the universe reveals and what our frameworks are prepared to accept, leaving open the possibility that the earliest structures did not merely form too fast, but formed according to rules we have not yet learned how to recognize.